Hello everyone, welcome to the video lecture of this course finite element method. So this is the second lecture of the fourth module, which is related to the two-dimensional elements and basically the vector variable problems. Now in the earlier lecture we have seen that the four basic sets of elasticity equations. Now among those four basic sets of elasticity equation, we have seen the stress-strain relationship equation, then the strain displacement equation, then the equilibrium equation, and the compatibility equation. So those were the four basic sets of the elasticity equations that we have discussed in the earlier lecture. Now after that we have discussed the concept of the axisymmetric elements, and we have seen the formula and the relation in between the stress and strain and the body factor in case of these axisymmetric elements. Now today in this lecture we will discuss the shape function and the stress strain or the strain displacement matrix for these axisymmetric elements, and based on those different formula we will try to discuss some numerical in the next lectures. So let us start today's lecture. So these are the course objective and course outcomes of this subject finite element method. Next it is the COPO mapping of this subject. So we will start with this slide, which states the derivation of the shape function for the axisymmetric element, which is actually a triangular element we will consider. Now to derive the shape function of an axisymmetric triangular element, we will consider that axisymmetric triangular element with nodes 1, 2 and 3, which is actually shown in the diagram. So that one we have seen earlier. Now let the nodal displacements be u1, w1, u2, w2 and u3, w3. So these are the nodal displacements that we have considered. Now the displacement u, it is actually a column matrix that consists of u1, w1, then u2, w2 and u3, w3. Now, since the triangular element has 2 degrees of freedom at each node, so that means it has 6 generalized coordinates. So the displacement functions u equals to a1 plus a2r plus a3z. Because in case of this axisymmetric elements, we consider the cylindrical coordinates, which is r, theta and z. So the displacement functions u equals to a1 plus a2r plus a3z and w equals to a4 plus a5r plus a6z. So these are the equations 4.17 and 4.18 respectively. And here the a1, a2, a3, a4, a5 and a6, these are the global or generalized coordinates. And let u1, this is equals to a1 plus a2r1 plus a3z1. Next u2 equals to a1 plus a2r2 plus a3z2. Next u3 equals to a1 plus a2r3 plus a3z3. Now if we write the above equations in matrix form, then in the left side of the equation we will be having a column matrix of u1, u2 and u3, and in the right hand side we will be having a 3 by 3 matrix. Now this 3 by 3 matrix consists of 1 R1 Z1, 1 R2 Z2 and 1 R3 Z3 multiplied by a column matrix of A1, A2 and A3. Now from this equation, if we want to find the value of the column matrix A1, A2, A3, that will be equals to the inverse of the 3 by 3 matrix multiplied by U1, U2, U3. So this is our equation number 4.19. Now to find the inverse of this 3 by 3 matrix, let D is that matrix, so D inverse it will be C transpose divided by the determinant of the D. Now first we need to find the cofactors of the matrix D. So to find the cofactors, C11 it is like a 2 by 2 matrix and the notation it is plus here. So it will be plus R2Z2 and R3Z3. So that is actually R2Z3 minus R3Z2. So this is the value of the cofactor, that is C11. Next we need to find the value of C12. So this is a 2 by 2 matrix. The sign is minus here. So 1Z2, then 1Z3. So finally we are getting Z2 minus Z3. So in this similar manner we can calculate all the cofactors of this matrix D. So in case of C13 we will be having finally plus R3 minus R2. Next for C21, the cofactor it is R3Z1 minus R1Z3. Next the cofactor C22 it is Z3 minus Z1. Then C23 it is R1 minus R3. Then C31 it is R1 Z2 minus R2 Z1. Then C32 it is Z1 minus Z2, and the last cofactor C33 it is R2 minus R1. So these are the 9 different cofactors for this 3 by 3 matrix. Now if we write the matrix with this all 9 cofactors, then it can be written and represented like this. Now CT it is actually the transpose of this matrix C. So this transpose operation it is known to us, so we can perform this transpose operation. That means a row column interchange will be there actually. So this is the C transpose, that is the matrix transpose we have performed here. So this is our equation number 4.21. Now we need to find the determinant of that matrix D. So to find the determinant, we can perform the matrix operation, and finally we are getting the equation number 4.22, which is the determinant of the matrix D. Now to calculate the inverse of that matrix, which is actually CT by D determinant. So we can put the values of the CT and the D determinant, and finally we are getting this equation. It is the right hand side of this D inverse matrix that we have represented here. Now if we substitute the D inverse value in the equation, then we are getting that the column matrix A1, A2, A3, this is equals to the D inverse multiplied by a column matrix of U1, U2, U3. So this is the equation number 4.23 that we have written here. Now, the area of the triangle, it can be expressed as a function of the RZ coordinates of the nodes 1, 2 and 3. So to calculate the area, A equals to half multiplied by the matrix of D. Now, to calculate the area, we can perform the matrix operation, and finally we are getting the 4.24 equation. So next, if we substitute the equation number 4.24 in equation number 4.23, then we are getting the equation number 4.25. So in the left hand side of this matrix of this equation, we are having the column matrix of A1, A2, A3, and this is equals to 1 by 2 A multiplied by a 3 by 3 matrix multiplied by another column matrix of U1, U2, U3. Now here you can take into assumption some other notifications for simplify this equation further. So that means in equation 4.26 we are having here as the left hand side of this equation we are having the column matrix of A1, A2, A3. This is equals to 1 by 2 multiplied by a 3 by 3 matrix multiplied by one column matrix of U1, U2, U3. Now in this 4.26 number equation we are having some variables which are actually alpha 1, this is R2Z3 minus R3Z2, then alpha 2, this is R3Z1 minus R1Z3, and alpha 3, this is R1Z2 minus R2Z1. So in the similar manner we can write the mathematical representation of B1, B2, B3 and gamma 1, gamma 2 and gamma 3. So here alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3 and gamma 1, gamma 2, gamma 3, these are the notations we have considered here for further simplification of the equation number 4.25. Now from equation number 4.17 we have seen that U equals to A1 plus A2R plus A3Z. Now we can write this equation in matrix form, that is U equals to a row matrix of 1 RZ multiplied by a column matrix of A1, A2, A3. Now this, in case of this A1, A2, A3, that column matrix, we can put its mathematical representation from the equation number 4.26 that we have seen in this earlier slide. So from this 4.26 number equation we have taken the formula of this A1, A2, A3 column matrix, which we have put here in this equation. So that means here will be a multiplication of 3 by 3 and 1 by 3 matrix So after performing this matrix multiplication, we are getting the value of u. It is a row matrix multiplied by a column matrix of u1, u2 and u3. Now the above equation, that is the earlier equation here, it is in the form of u equals to n1, n2, n3, which are the shape functions multiplied by a column matrix. So a row matrix multiplied by a column matrix. This is the in general form of the earlier equation for the displacement u. So and w can also be written in the similar manner, which is n1, n2, n3, that row matrix multiplied by a column matrix of w1, w2 and w3. So these are the two equations, equation number 4.27 and equation number 4.28 we are having here. Now here, what are these n1, n2 and n3? So these three are the shape functions, and the formula for n1, it is alpha 1 plus beta 1 r plus gamma 1 z divided by twice a. Then n2, this is equals to alpha 2 plus beta 2 r plus gamma 2 z divided by twice a. And n3, this is alpha 3 plus beta 3 r plus gamma 3 z divided by twice a. So these are the three values for the mathematical representation of the shape functions. Now we can write the earlier equations 4.27 and 4.28 as u equals to n1 u1 plus n2 u2 plus n3 u3, and w equals to n1 w1 plus n2 w2 plus n3 w3. So these are the equations 4.29 and 4.30 we are having now. Now if we assemble these equations in the matrix form, then we are getting the displacement function u, function of rz. This is actually a column matrix of u rz, w rz. So this is equal to a 2 by 6 matrix multiplied by a column matrix. So this is our equation number 4.31 for the displacement function. Now that formula we need to remember to solve the numericals based on these two-dimensional vector variable problems. Next we are having the strain displacement matrix, that is B, for axisymmetric triangular element. Now the formula for the displacement function for axisymmetric triangular element we have discussed just now, that is the displacement function u rz. This is equals to a column matrix of u rz and w rz. So this is equals to a 2 by 6 matrix multiplied by a column matrix, or we can write u equals to n1 u1 plus n2 u2 plus n3 u3. This is equation number 4.32, and w equals to n1 w1 plus n2 w2 plus n3 w3, which is our equation number 4.33. Now the strain components we need to find here. First we need to find the radial strain, it is ER. This is equals to del U del R, which is del N1 del R U1 plus del N2 del R U2 plus del N3 del R U3. So this is the mathematical representation of the radial strain. Next we need to find the circumferential strain, that is E theta. This is equals to U by R. So this E theta, it can be written as N1 U1 by R plus N2 U2 by R plus N3 U3 by R. So which is our equation number 4.34. 4.35, and this is the mathematical representation of the circumferential strain. Next, we need to find the longitudinal strain, which is Ez equals to del W del Z. So Ez equals to del N1 by del Z into W1 plus del N2 del Z plus W2 plus del N3 del Z W3. So this is the mathematical representation for the longitudinal strain. And finally for the shear strain, comma Rz is equals to del U del Z plus del W del R. Next we are having the equation number 4.37. It is for the shear strain mathematical representation. If we arrange these equations 4.34, 35, 36 and 37 in a matrix form, then we are having the equation number 4.38. And this is a very complicated formula of the equation that we need to remember by practicing a lot. Now from equation 4.27 or 4.28, we know that the value of the shape functions n1, this is equals to alpha 1 plus beta 1 r plus gamma 1 z divided by twice a. Next n2, this is equals to alpha 2 plus beta 2 r plus gamma 2 z by twice a, and n3, this is equals to alpha 3 plus beta 3 r plus y plus gamma 3z divided by twice a. So these are the mathematical representation of the shape functions with n1, n2 and n3 for the triangular axisymmetric element. Now if we perform the partial differentiation, then we are getting del n1 del r, this is equals to beta 1 by twice a. Then del n2 del r, this is equals to beta 2 by twice a. Then del n3 by del r, this is equals to beta 3 by twice a. So n1 by r, this is now 1 by twice a alpha 1 by r plus beta 1 plus gamma 1 z by r. And n2 by r, this is equals to 1 by twice a alpha 2 by r plus beta plus gamma 2 z by r. Next n3 by r, this is equals to 1 by twice a alpha 3 by r plus beta 3 plus gamma 3 z divided by r. Now del n1 del z, this is equals to gamma 1 by twice a. Then del n2 by del z, this is equals to gamma 2 by twice a. And del n3 by del z, this is equals to gamma 3 by twice a. So these are the partial differentiation that we have performed for the shape functions here. Now if we substitute all these partial differentiation values in the equation number 4.38, then we are getting this equation where the various kinds of stresses are here in the left hand side of this matrix, and in the right hand side you can see 1 by twice a multiplied by 3 by 6 matrix multiplied by a column matrix. Now the above equation, it is actually in the form of the strain matrix is equals to B into U. So here this B, it is the strain displacement matrix. This B, it is the strain displacement matrix here. So we can see from this equation number 4.39, the formula for the strain displacement matrix. So this is actually a 4 by 6 matrix. In this matrix, alpha 1, this is R2 Z3 minus R3 Z1. Then alpha 2 is R3 Z1 minus R1 Z3. Alpha 3 is R1 Z3 minus R2 Z1. Next, beta 1, this is Z2 minus Z3. Then beta 2, it is Z3 minus Z1. And beta 3, it is Z1 minus Z2. Next, we are having the gamma 1, this is R3 minus R2. Then gamma 2 is R1 minus R3. And gamma 3 is R2 minus R1. So this is the formula of the strain displacement matrix that we have seen here. Next, we are having the stress-strain relationship matrix D for the axisymmetric triangular element. So all of you have studied the concept of the stress, strain and the Hooke's law in earlier semester when we have studied the strength of material. So by using the Hooke's law, we derived the following normal stress equations, which is actually sigma x, sigma y, sigma z and tau xz. Now if we substitute x equals to r and y equals to theta in the above equations, in that case radial stress sigma r, this is equals to E, that is the Young's modulus divided by 1 plus b into 1 minus 2b multiplied by ER into 1 minus b plus b E theta plus b z. This is equals to 4.40. So this is the Poisson's ratio, actually this b or the nu. Next we can write the formula of the circumferential stress, which is sigma theta. And this is our equation number 4.41. Next we are having the formula of the longitudinal stress, which is sigma z, and here we are having the equation number 4.42. So these are the formula for the radial stress, circumferential stress and longitudinal stress. Next we need to find the formula for the shear stress. So the formula for the shear stress, tau rz, this is equals to E by 1 plus b into 1 minus 2b multiplied by 1 minus 2e by 2 into gamma rz. So E is the Young's modulus and beyond nu it is the Poisson's ratio. Now if we arrange the above equations, that is 4.40, 4.41, 42 and 43 in the matrix form, then we are getting in the left hand side of the matrix all the stresses like the radial stress, circumferential stress, longitudinal stress and shear stress. And in the right hand side of this equation we are having a 4 by 4 matrix multiplied by the strain ER, E theta, Ez and gamma rz, that column matrix. But this equation, it is in the form of sigma equals to D into E. That sigma is the stress, D is the stress strain relationship matrix and E is the strain. So that means from this comparison we can say that the stress strain relationship matrix will be mathematically represented as the equation number 4.45. So this is the final representation of the stress strain relationship matrix. So these are the topics that we have discussed in this lecture. So first we have discussed the derivation of the shape function for the axisymmetric element considering the triangular element. Next we have discussed the strain displacement matrix for the axisymmetric triangular element. And lastly we have seen the stress strain relationship matrix, that is D, for the axisymmetric triangular element. So these are the three different topics that we have discussed in this lecture. In the next lecture, we will discuss the element stiffness matrix and the Galerkin approach. So this is the end for this lecture.